Hi guys, in this video I want to talk to you about the center of mass and show you kind of an application of it. So I have here a video, and it's essentially two air hockey pucks connected together by a rod. They're moving in some kind of complicated motion. It doesn't look that complicated, but if you were to zoom in on any of one of the pucks, it's a little bit complicated. I want to just say this is the axis. It's slightly tilted, but if you zoom in on this guy, there's motion in the up-down direction as it swings and to the left. And neither of these are steady. So let me just turn on mass 1. I said it's a mass of 1 kilogram. I don't really know, but you can see its motion in the horizontal direction. It kind of speeds up and slows down in the horizontal, and it moves up and then down in the vertical. So kind of a complicated motion. It's not anything we've looked at. It's not anything neat that you can fit a function to. What about mass B? It's kind of a similar story. Moves to the left, kind of speeds up and then slows down, moves down and then up. And the graphs for it are that. Let me just play that again. So steadily moving to the left, but kind of speeding up and slowing down, and then move down and then up. All right, so that's kind of a complicated motion. If only there was a way that we kind of simplify this and we can introduce the center of mass. So I've already kind of created it. Let me just do it again. I can go to New, Center of Mass. I can select the masses. Because they're both 1 kilogram, the center of mass will just be a point halfway between. And now see if you can tell the motion of it as it moves across. Visibly, hopefully you can see, it's kind of just a nice steady line. And you can see the graph on the right. I'm going to show both the vertical and the horizontal. Play it one more time. So you can see in the horizontal, it's moving just at basically a constant speed. It's a straight line. And in the vertical direction, you can see it's like on the order of 5 centimeters, -5 centimeters. Whereas in the x direction, it's like 1,000 centimeters. So like the vertical motion is almost negligible. I would say to a good precision, this is moving at a constant velocity in the horizontal direction. I've tilted the axis just a little bit just to make that vertical motion as small as possible. So this kind of simplifies the analysis of the center of mass. If I know their distance from the center of mass at any moment, I can kind of calculate it. But it's easier to just look at the center of mass. This two-body system right here doesn't have to be air pucks connected by a rod. It could be a planet orbiting a star or two stars orbiting each other. It's often simpler to switch to the frame of reference where the center of mass moves at a constant velocity. Basically, nothing is acting on the center of mass from outside. The friction is negligible because of the air. This is on a flat surface, so gravity is basically ignored. So the center of mass, then when there's no external net force, it's going to move at a constant velocity. It's kind of easy to look at things in that constant velocity frame of reference, that point of view, to then do your analysis. And in AP Physics 1, switching to that point of view of the center of mass, what is it doing? Basically, if there's no external net force, it should be moving at constant velocity. And from that, you can kind of say, hey, if I know where one point is, I should be able to predict where the other point is. If mass A is 2.5 meters to the left, then mass B should be 2.5 meters to the right, if I know where the center of mass is. So we'll use this idea in practice. Hope that was helpful. See you around.